So I want to take a brief time to think about power here. Normally, we try to make connections with amounts so you have a better idea of what we mean by an amount of something. So to do this with power, we want to walk you through some sort orders of magnitude with power to sort of make sense of what a kilowatt means and what a gigawatt means. So to start with, one unit of power that doesn't immediately come to mind but is always on our minds is that the average person eats about 2,000 calories a day. This is just an estimate, and the dietary calorie is really the kilocalorie, so you do have to be careful with units if you're doing unit conversions here. In any case, 2,000 dietary calories per day is a power. It's amount of energy divided by a time. If we convert this to watts, it comes out to be about 100 watts. That is the power of an old-style light bulb, but it is typical power output of a person. If you have a massive amount of muscle and are very active, or this may be much larger. I've heard about athletes with diets that are 3 to 4 times this amount, but for an average person, this is about right. So our caveman here, who uses no other power sources other than what he eats, runs about 100 watts. For comparison, how much does it cost to run a 100-watt light bulb for 1 year? Well, to do this, we multiply 100 watts times the number of hours in a year, so 365 days and 24 hours, and then multiply that by 1 over 1,000 to get to kilowatts, and then multiply that by the cost of electricity, which is about 10 cents per kilowatt hour. So if we do this, this comes out to be a price of about $88, or we'll say roughly $100, because we're sort of just estimating things here. This is useful because it tells us that to run 1 watt of electricity for 1 year costs about $1. This allows us to convert power into money, since you may not have a great intuition about what a megawatt is, but if you know it costs $1 million a year, then you probably have a better feel for it. So next we have 10 kilowatts, which corresponds to the power usage of an average American. This means that the power you typically use is about 100 times that of the minimum that you need. This is about twice the developed world average, and if it was all electricity, it would cost $10,000. Now, a lot of this may be cheaper than the cost of electricity, say heating oil to heat your place, but in general, it corresponds to 10 hair dryers going 24 hours a day. So 100 times the power of an average American is 1 megawatt, and this is the power of a windmill. A typical land-based windmill produces about 1 megawatt of power, so each of these windmills produces about $1 million a year, or it produces enough to power 100 Americans. That is sort of impressive, but it does mean we would need something like 3 million some windmills in order to power the country. 1,000 times the power of the windmill is a nuclear power plant at 1 gigawatt. So that means that a nuclear plant produces enough power for 100,000 people, so a small city, and the price of $1 billion a year. So the point is that we can convert our power into a price of electricity so we can get a little better intuition about what some of these numbers mean. So next we want to think about the amount of power and the amount of work done in an electric circuit. So we know that the magnitude of the work done is the charge times the potential. That means that the power is the charge times the potential divided by the time. Notice the charge divided by the time is the current, so that means we can say that the power is equal to the current times the voltage. So that gives us 2 big formulas for trying to understand voltage and power. We have Ohm's law, which gives us that the voltage is equal to the current times resistance, V is equal to IR, and the power, where the power is equal to the voltage times the current. We can then combine the two. If we know the voltage and the resistance, then the current is V over R. So plugging that in gives us the power to be the voltage squared divided by the resistance. Or if we know the current and the resistance, so in that case, then we use V is equal to IR and plug that in to get the power is equal to the current squared times the resistance. All of these are equivalent, assuming we're talking about a standard resistance circuit. Okay, so now we want to solve some problems. We have a 60-watt light bulb, and the voltage is 120 volts, and then we want to know what is the current. Well, we have the power and the current, so power is equal to current times voltage. So we divide the power by the voltage to get the current, which is 60 watts over 120 volts, which gives us 0.5 amps. Next, we want to know how many light bulbs we can plug into our room. So if it has a limit of 10 amps, well, each light bulb needs 0.5 amps. So 20 bulbs times 0.05 gets us to the 10 amps. So we have a maximum of 20 bulbs on our 10 amp circuit breaker. Okay, so you guys have a few problems to do, and next we're going to take a look at resistors.